All right, students, here we go. Thermochem homework number 5. This is the last one. Question number 1. Using the heating curve for water right here, we're going to write increasing, decreasing, and steady in each box for temperature, kinetic energy, and potential energy. We tell what formulas we use in thermochem, and we can also tell what phase things are. Now, this is a heating curve. We know that because we start out with low temperature and we go up to high temperature. Now, what's important about this graph? Well, this graph's in centigrade. We have this temperature called the freezing point, or in a heating curve case, it's the melting point. And also at 100 degrees centigrade, we have what's called the boiling point. The two most important temperatures are the phase change temperatures. We have the cold phase change temperature, in this case it's melting, and we have the hot phase change temperature, in this case it's the boiling point. And then we have the rest of the graph. Now from A to B, we have ice that's super cold. It gets warmer and warmer until it gets up to point B. From B to C, it's changing from solid to liquid. That's called the melting point. Now what temperature is BC? BC is flat. It's at one temperature, 0 degrees centigrade. Now, what's happening to the kinetic energy if the temperature is 0 degrees and steady? That means the kinetic energy is steady also, because temperature and kinetic energy always do the same thing. But we're adding heat. Look at that. I put in 3 Ds because I'm so excited. Adding heat. If we're adding heat and the kinetic energy won't go up, that means the potential energy increases. And that makes sense because it's going from solid to liquid, and liquids have a higher potential. Now, what formula would we use in thermochem to melt something? We would use this formula, Q equals mH of F, the heat of fusion formula. Now, from C to D, it's a liquid here, and it's a liquid here, and the temperature's going up. So from C to D, it's actually in the liquid phase only. The temperature, it's increasing and increasing, and that means the kinetic energy is increasing. And since the kinetic energy goes up, this will be steady. We don't need potential energy when there's a temperature change. Now, what formula do we use to go, say, from here to here, or from here to there? We use this formula, Q equals MC delta T, because there's a change in temperature. Look here, no change in temperature, 0 degrees. Here, change in temperature from wherever to wherever else. Now, E to F, we're going to go E to F over here. We're not going to do D to E. This is E to F. So from E to F, we're only in the gas phase, right? Because it's liquid, it becomes a gas. By here, it changes, and then it stays a gas. The temperature is increasing again. Temperature goes from 100 up as high as you want to make it. That means the kinetic energy is going up also. And if the kinetic energy goes up, the potential energy is steady. And that makes sense because it's gas and it stays a gas. Now, what formula are we going to use over here? Now, this actually is a little bit strange. We're going to use Q equals MC delta T, but the C gets an exclamation point. The C value here is different for steam than it is for liquid water. Okay? It's still going to have a change in temperature from E to F, but it's not going to be 4.18 as a constant. It's going to be lower. And that number, I believe, is 1.9. I don't remember that number offhand, but give me 2 seconds. Yeah, I believe it's 1.9, but it'll have to be given to you. It's not actually part of the class, but it's not the same. Liquid water is different. Ice and steam have different specific heat capacity constants. Now, some other questions here. Why is BC shorter than DE? Why? And use these numbers in your answer. Over time, heat is added at a constant rate. To melt takes less energy than to vaporize. Now, if we add heat at a constant rate, let's just, I don't know, we'll call it something 50 joules per second. All right, we're adding 50 joules per second. It's going to take a certain number of joules to melt the ice. Depends on how many grams you have, but at 50 joules per second, it's going to be at a steady rate. Now, to boil something, it takes a lot more energy. It takes the heat of vaporization constant instead of the heat of fusion constant. In order to get 50 joules per second to get up to 2,260, it's going to take a longer period of time. So since heat is being added at a constant rate, if it takes less energy to melt, it'll take less time. To vaporize, since it takes more energy per gram, it's going to take more time. Now, in this next question 3, what formula do you use to go from D to E? D to E. We're going to use Q equals mH of V. We're going to vaporize that water. Now, what formula do you go from C to D? That's in the middle. That would be Q equals mC delta T, because there's a change in temperature. And then finally, to go from B to D. B to D, look at that. B to D. Here, we're going to first use Q equals mH of F and Q equals mC delta T. We're going to have to do it in 2 steps. First, we're going to have to melt the ice from B to C. That takes energy. And then it takes more energy to warm the water up all the way up to the boiling point. So that's a 2-step problem, and we add these joules and those joules to get a total number of joules.